Well, welcome to TE Sessions. My name is Sarah Storer. I'm an Outreach Project Manager here at RoboJackets, Georgia Institute of Technology. And today we have Vision Tracking with the Robo Alliance, Team 1261. And I'll hand it off to them if you can give them a round of applause.
Hi, I'm Chris Carlson, lead programmer of Team 1261, and with me today are Shav Sarkar and Terry King, and we're going to be giving a presentation on vision processing. So what we're going to be going over in this presentation is an overview of what vision processing is, why we use it for this year's competition, how we implemented it, and tips for how to implement it yourself in your own robots, what we learned through our process, and how that can apply, what's next, like what we want to do, what we could have done better, and then we'll have some time for questions at the end.
So before we actually start the meat of the presentation, we want to cover some common terminology that we might use during the presentation so that we are all sort of on the same page. To start us off, first thing we have to define is what a contour is. And contours are basically a boundary of pixels that surround all the pixels in an image that have a similar color. So if you have an image, all the pixels with, let's say, red that are right next to each other, they'll all get bounded together into one contour. And what we can do is we can treat that contour like an object. We're going to go into the specifics of that later, but you see that word, just know what it is. Second thing is offsets. So ideally, in this perfect sort of FRC world, the camera would be right next to the shooter arm that shoots the projectile at the target. So what we would do is the center of the camera frame should be the crosshair, the center of where the shooter is going to shoot. So the offset is the distance between the actual target in the frame of a camera to the center of the camera. So ideally, we would try to minimize that offset as much as possible. So that's the definition of offsets here. Shot arc is something relatively simple. When you shoot a projectile, there's gravity affecting it. There's some distance that it's going to actually fall vertically. So that value accounts for that drop in distance. Network tables, it's a system to pass data between the robot and the computer on the same network. It's an FRC thing, and we're going to talk about why we use that and how we can sort of improve on that later. PID controller, it is a control feedback loop that can be used to accurately move motors to different positions. We use that to actually control our drivetrain, and we're going to talk about how we input sort of image data into that PID controller system later, so that's why that's up there. HSV, it's a way of representing color in computers, and it's very similar to something like RGB, red, green, blue, except it's a bit more human readable. I'll get into like how that works and why later, but that's just what that means. So this is just an overview.
Okay, so the first question for vision processing with robotics is why would you want to use it? So for Stronghold specifically, the high goals gave a lot of points, but they were higher up, they're very small. It's almost impossible to aim at them manually without having a very predictable shooter like a catapult where you line up at a certain spot. And even if you do have one of those systems, the obstacles were typically very tall, the portcullis, the drawbridge, they would obscure driver vision. It'd be very hard to actually see where your robot is so you can line it up properly. So we decided that our best course of action would be to have our robot automatically align and shoot for us.
So in order to actually implement that vision processing into the game, these are the general steps that we knew we had to take. So the first one is we needed to find the target in an image. The camera is going to give us a particular frame, and we have to say, how do we find that object, and how do we get the useful data out of it? So once we get that useful data, we need to somehow figure out how to transmit that data to the actual robot. And we'll get into how that works in a little bit. And then the third step is the robot needs to aim. So somehow the robot needs to take that data, convert it into some positional and rotational data for the robot to move and aim. And the fourth step, and the one that everyone likes, is it has to finally shoot. And that's how it and that's the general flow that we want this whole system to take.
So in order to do this vision tracking process, there are a couple of questions we need to answer. So one of them is, where do we do the image processing? So there are a couple of options we have. One of them is the RoboRio itself, where yeah, you run the robot code and the vision tracking code simultaneously. Then another place you could run it is the driver station laptop, and a third place is a coprocessor, such as a Raspberry Pi or an NVIDIA Tegra. And we'll cover the pros and cons of this soon. Another question that we have to ask is, how do we do the image processing? There are a couple of platforms we can use, and we'll talk about grep and Python plus OpenCV in a later slide. And a third question to answer is, how do we implement the image processing? There's a couple of factors you need to consider when you're doing this image processing. One of them is computing offsets. As we talked about earlier, offsets include the vertical and horizontal offsets of how far your camera is from the shooter, as well as for your vertical offset, you may need to consider the shot arc, and that depends on the distance away from your target, and like I said, the horizontal offset is based on the camera distance from the shooter. Another thing you need to consider is your input to the PID system, which will allow you to actually align your robot properly and shoot the boulder.
So where do we actually do the image processing? So I know Rishabh just mentioned how we could do it on the RoboRio laptop and coprocessor, and this is the slide to talk about it. So the first and most obvious one is, why don't you just run the image processing on the RoboRio itself? Now, that's the thing that runs all the robo code, put the image processing code on that too. And there's some benefits to this. The first and most obvious one is there's absolutely no latency. It's all in one process between the robot code and the image processing code. Now, the issue is it really spikes the CPU, and we don't really, an important thing to consider is that image processing shouldn't be like the main focus of your entire robot. It's a feature. It's supposed to supplement and improve the robot. So if the image processing is somehow bringing down the robot's performance, you're doing something wrong. So we were really considering, we didn't want to spike that CPU of the RoboRio. So ultimately, we decided that we needed to offload that process somewhere else. So RoboRio wasn't the place to do it. The second thing is we could just do it on the laptop, the driver station. And that has some benefits. It gives us processing power. There's already an existing framework for communication between the RoboRio and the laptop, so easy communication. So it will be relatively easy to implement. And we can very easily implement other features, such as adding a live feed for the driver team of the video feed. Some downsides to this, though, is that there's relatively high latency between the image process code and the RoboRio. We're sending it over the network, and that can take some time. And plus, FRC sets a data cap on the amount of things you could send. I think it's around 7 megabits. And once you get to 6 megabits, it actually slows down significantly. So we didn't want to do it on our driver station laptop because we were afraid, again, that latency issues would sort of cause the whole image processing process to fail. So the third and final step, the third process that we decided to go with is that we could put this whole image processing thing on a coprocessor. And that is a second processor besides the RoboRio on the robot itself. So this could be something like a Raspberry Pi and NVIDIA Tegra. These are all sort of small, computer-on-a-chip platforms. So we could put that on a RoboRio and have the processing on there. And that has similar benefits to the laptop. First of all, there's processing power. It's a completely other system. Lower latency than the laptop because we're directly connected to the RoboRio. So we can send bits however many we need. And we can sort of build a reliable network. Because it's on the robot itself, we can custom build our own little network and actually have a reliable way of communicating. We also have GPU flexibility. So if you're trying to run a really complicated image processing program, and way complicated than what we were trying to do, you can actually have something like the NVIDIA Tegra, which has a ton of GPU power, and actually use that to do your image processing. Now, some downsides to having a coprocessor is that we're adding extra complexity to the whole entire process. Because the robot's not really built for any of this. We would have to build it from the ground up. So we would have to build custom communications and sort of a custom pipeline to put this entire thing to. Ultimately, we decided to use the coprocessor because of the lower latency and the more processing power it gave us. More specifically, we chose to use the Raspberry Pi because Raspberry Pi was both inexpensive and available for us. So how do we actually do the image processing? Now that we know where to do it on, how do we do it? Well, there's basically two main methods of doing image processing for this season. and one was using GRIP, which was the software that FRC provided in order to actually do image processing. And the other version was we could try building it ourselves using an image processing library such as OpenCV and some programming language, in this case Python. This was really our first time doing image processing on this scale and this sort of complexity. So we decided to take, when we were researching how we could do image processing and implement it, we took a divide and conquer approach. So what we did is we had some people on the programming team work with GRIP on the laptop, some people worked with GRIP on the Raspberry Pi, and some people actually worked with OpenCV and Python on the Raspberry Pi. And we would experiment to see which one ultimately proved to work out the best. In the end, it was Python and OpenCV on the Raspberry Pi. And here's some of the reasons why. So one of the benefits to GRIP is that it's very easy to use, has a very nice GUI. It's a software application. It's easy to test, but even though it has some functions of OpenCV, it doesn't have all of them. So you don't have access to that full image processing library as you may want to. And plus, it's new, so it's relatively untested in certain cases. Especially when we were testing it, GRIP wasn't even really available to run on the Raspberry Pi, on that co-processor. So ultimately, we sort of left GRIP behind. Now, some of the benefits to using Python and OpenCV, on the other hand, was you had access to all of the OpenCV functions. You could do some things you can't do on GRIP, such as you can draw on the image. So let's say you can draw, targeting dots, and you can draw rectangles around the target, all sorts of other stuff, like advanced contour filtering. So you can be a bit more specific in how you're filtering all of your objects in an image. You can set a certain max area size, and maybe you can set a certain ratio between the area size and what the actual, the width of the target is. Now, plus, you get all the benefits of this is an actual programming language. You have better code structure. You can sort of custom build your actual, structure of the code. And plus, in that sort of last comment is a silly one, but it's relevant in that when I say Stack Overflow, we mean that it's tried and true, that this system existed for a relatively long time, and people have put example code online, and there's a ton of documentation on what you can do and how you can do it. Like I said, GRIP is relatively new, and so we weren't really sure what the possibilities were, and it was constantly changing. So we decided to ultimately go with the Python and OpenCV route on the Raspberry Pi, as that it was very, tried and true and very reliable in that sense. So how do we actually implement the image processing? So in order to actually do the image processing, we decided to actually use something called HSV thresholding. And what HSV is, it's a different way of representing color for computers than something like RGB. So these are the color spaces for HSV and RGB right next to each other. So HSV, like RGB, is just 3 numbers: hue, saturation, and value. So hue is that sort of outer rim thing. And hue sets the color, the actual tone or hue of the color of the pixel. So it's what determines whether if it's green, yellow, or red. Saturation sort of determines how vivid that color is. The closer to the center it is, the more white it is. The farther out, the more sort of vivid that color is. And value represents its sort of darkness level. It go down and it gets darker. Go up, it gets sort of back to that color spectrum. This is the RGB cube. What you can imagine is that sort of one of the axes is red, one of the axes is blue, one of the axes is green, and you move in that 3D space to set all of your color. Now, the reason why this differentiating these two different ways of representing color is important is that for us, humans, it's a lot easier to actually use HSV than RGB. Because using HSV, you know that changing one color inherently does something to the pixel you're actually affecting. You know that if I'm changing value, that I'm actually affecting its brightness. You're moving up and down. If you want to make a pixel darker using RGB color spectrum, you actually have to move it in a weird diagonal way in the 3D color space. So that's what the HSV and RGB sort of difference is. And the reason why I make that difference is that in order to actually find that target in our image, we use something called HSV thresholding. Basically, take an image. Images are just basically made up of a huge array of pixels, right? Every pixel is a certain color. And we say, filter out all the pixels except pixels of this certain color. And what we can do is that if you have a camera pointing at the target, remember the target is actually surrounded by something called retroreflective tape. If you shine a light towards the retroreflective tape, the light bounces right back towards the light source. So if you have a camera right next to the light source, then if you shine a green light towards the retroreflective tape, the green light's going to come back to the camera. And so what you can do is that the target's surrounded by retroreflective tape. If you have a green LED next to the camera, you point that camera and turn the LED on to the target, that target in your frame is going to look very, very sort of green. And then you can use this HSV thresholding that I was talking about to actually pull only the green pixels out, rather than actually have the other pixels in here. So we have a small demo of that we can do over here. Can you click on that video?
Can you make it a little smaller so you can't see the top sliders?
Okay, so this is me in my bedroom. So that up there, oh crap, oh sorry. Oh, sorry, I didn't realize that was on a green laser pointer.
Okay, while we work this out, I'm going to answer a few questions from online. So we have somebody asking if the Raspberry Pi 3 would work well with the RoboRio. And in our experience, yes. We can't give any advice on grip because, as we said, we chose not to use that because when we used it, it was not currently supported very well on Raspberry Pi. But we personally use the Raspberry Pi 2 and Pi network tables to run our code alongside our RoboRio. Pi network tables is basically is Python compatible version of network tables. It allows you to communicate back and forth between the two. So your Raspberry Pi 3 should work out just as well. You just have to have the correct version of Pi network tables to go with it.
Okay, thank you. So can we have the demo play again? Sorry about that. So you should see 6 sliders. The first 3 are your lower bounds, and the bottom 3 are your upper bounds. And then it goes hue, saturation, and value for both of them. And as you can see, as I'm adjusting these sliders and setting my hues and setting my saturation, I can very clearly sort of separate that sort of very neon green square from the rest of the background. So this is the general process, and I'm shaking it around to show you how stable it is, I guess. So this is the process that I would use to actually find that object from those frames, the camera frames. And it's actually a very relatively simple way of doing it. So yeah. Can you click back on there? Alt tab back on there. Great.
So that's how the HSV thresholding works. Now let's put it all together in an actual pipeline for how be the current elevation plus the y offset that we got from the camera, and the target heading would be the current drivetrain heading plus the x offset that we got from the Pi. Then we would set those as our PID targets for our elevation and our drivetrain subsystems, which would move the shooter and the robot closer to the goal until we can actually shoot the boulder. So here we have a live demo of our autonomous. So this shows our program in action. So.
Just a sort of disclaimer, this was our very first time actually trying this Auton and it working. So I want you to notice these little 3 programmers up here trying to walk over, and the robot that's about to go under the logo, the low bar, whatever, that's our robot. And I'm just gonna, look at us a little. Okay. So that's us. Okay, our robot's starting. That's our mentor, sort of walking by, also anticipating. And we're running over. Our little robots are aiming. That was a good day.
All right, so after doing all of this throughout the season, here's what we learned. So there are a couple of things that we learned that you have to be aware of. So one thing is that the competition field will block MDNS. So if you try to resolve something like RoboRio 1261 frc.local, that won't work, and you will not be able to connect to your robot. So you should assign everything a static IP so that you can actually code in the static IPs and talk to everything during the competition. Another thing to be aware of, IP cameras boot slowly, so you need to make sure that you're connected to the IP camera if you are trying to use it in your vision code. So the thing that you can do, for example, is you can run a ping to the IP camera repeatedly, and once you get a reply from that, you can start your vision code then, and that will ensure that you can talk to your IP camera before your vision code starts and you don't crash your vision code. Another thing to be aware of is if you use multiple USB cameras on the Raspberry Pi, we don't recommend doing that because it's very complicated to try to identify which camera is which. There are ways of doing it, but the thing is when you try to, if you're trying to identify the camera using dev/video0 or dev/video1, those IDs are assigned randomly. So you'll need to have some other way to identify it, and that gets tricky. So we recommend that you don't put 2 USB cameras on the same Raspberry Pi at all. Third thing to be aware of, if you're writing images to the disk to stream them to your driver station, you need to make sure that your Raspberry Pi is using the RAM, not the SD card, to write those images to the file system. So what we did was we used RAM temp so that when we wrote our images to the temp directory, they would be going to RAM and not to the SD card. The reason we do this is because if we're constantly writing images to the SD card, we need to, if we're constantly writing images to the SD card, we will be wearing out the SD card quite quickly. And this actually happened a few times throughout our competition season, where since we were not using RAM temp, we were destroying multiple SD cards. So yeah, make sure that if you're writing images, you're using RAM. Another thing to be aware of, you should have a method of making sure that your coprocessor, your Raspberry Pi, is shutting down safely. So if you do not, if you just cut power to the Pi without shutting it down properly, you risk losing your data, corrupting your file system, and maybe damaging your hardware. So make sure that you have a way that at the end of the match, the Raspberry Pi will know to shut down so that you don't lose any of that. And then lastly, back up your SD card, make multiple backups of your SD card, regularly test your backups of your SD card. Don't go without backups because you never know when your SD card will die. And backups were kind of what saved us when, as I said earlier, we lost multiple SD cards since we were writing images to them so frequently. So we had to use those backups very frequently. So yeah, make backups.
Okay, So along the lines of testing all your code once you have it deployed and you're on the field and you're between matches and something breaks, is you need to have a very thorough system for debugging. So what our main system of debugging, since we don't have a real framework yet, was we used a system like Bandicam, basically a free screen recording software, and we took a recording of every match's driver station screen. So we could see what was going on, what were our stats, connection status, all of that. And the way we took advantage of that was we had several ping commands going on command prompts. So we'd have two different command prompt windows open, one pinging our Raspberry Pi, one pinging our RoboRio. And with those, we could tell if we lost connection to either of them. So we could see if we were simply losing our signal during matches when something like that went wrong, or we could see if we were just, our Pi was cutting out or some other odd issue. And then we would also have system.out.printlns that would basically write messages to logs from our code so that whenever we ran an automatic function like our automatic target and shoot, we would be able to tell what phase it's at. So if our drive team came to us and told us, hey, this isn't firing, we press a button, we can look back at those recordings, see those logs, and tell if it's actually getting stalled somewhere in the process. So like, are we getting stalled at shooting, at aiming, or if they just didn't press the button that time. And then, important to note, a lot of times you might have random anomalies, like just occasionally your program doesn't boot up or it crashes. And this kind of links back to the IP camera thing. These are usually race conditions, where one part of your system isn't ready when the other part is and tries looking for it. So with IP cameras as an example, we helped out another team that we're friends with at Worlds, and their robot, their vision tracking on the Raspberry Pi wasn't working all the time. They told us that just randomly it wouldn't work. And so I was over there trying to help them. We were looking at it. He would boot it up and it wouldn't work. And he'd go over and he'd restart the Raspberry Pi, not the rest of it, but only the Raspberry Pi. And then after he did that, the code would start working again. And they had no idea what was going on. So what was actually happening is, when you boot up the entire robot, everything powers on and starts its boot up process. And the Pi would finish before the IP camera was ready to run. And so as soon as the Pi was finished, it would go, okay, well, let's go pull this IP camera and start doing our stuff. And when there was no IP camera to pull, it would crash. And then, since he was trying to fix that problem and he didn't realize it was an IP camera causing it, he would simply reboot his Pi, which would then reboot and then find the now booted IP camera and work properly. So like Rashad said earlier, you want to have pings to ensure that what you're looking for is there before you access it. Okay, so now for some hardware design concerns. A lot of these are mostly planned. You do on the fly, but you need to be aware of these when you're designing your robot, because if you go halfway through your season, you have this beautiful code, but your build team doesn't know that you're writing it, then they're not going to have any space to put your stuff on the robot. So the first thing you need to make sure of is you have space on your robot for both your LED system and your camera. So these need to be a very robust mount. They need to be well placed on the robot so they're as near to the shooter as possible, because if they're going to take hits. This is Stronghold that we were playing in, a very rough game. And so when they take hits, they need to be able to not get moved or shifted, especially in the case of the camera. If your camera gets bumped even slightly, your longer range shots are going to start missing just ever so slightly. We got tripped up at World because of this. Our camera was slightly bumped after a match, and our shots kept bouncing off the left edge of the goal instead of going in. And then you need to make sure with your LEDs that they're properly secured. We have a very, very strong LED. We ended up using a diving light. It was probably a little overkill for the purpose, but it worked. But we saw most teams using LED rings and such, and those are typically fairly fragile. They'll break if they get hit too hard, and that's probably bound to happen when they're on a shooter instead of hanging up in the air away from the robot. So make sure your LEDs are in a secure place or just strong enough to not get broken by strong hits. And then another important thing to consider that you usually won't notice until it's too late, your wiring. So especially for flywheels, the flywheel shooters would move up and down and they would aim, and that involves a lot of moving parts. And when you have a camera on there, that camera has to be plugged into your system. And if that wiring just kind of goes wherever it wants and isn't well placed, it's going to get cut when it rubs against other pieces. We ended up losing one or two cameras to cables that were just mostly sawed through and were having spotty connection. So basically, when you're wiring up your cameras and stuff, make sure they go basically inside something if possible, so they're protected. Because if those get cut, then you're going to be in trouble. They'll have weird issues, and you'll try debugging it for a while, only to find that it was actually a physical issue. And then another important thing with LEDs, make sure the LEDs are right next to the camera. With retroreflective tape, the way it works is you shine a light at it, the light hits the retroreflective tape and comes right back at it. So it's not like a mirror. It's not like a normal mirror where if you're looking at another angle, you can see it. If your LED isn't right next to the camera won't even see the light. It'll, like we would move ours like a foot or two to the side, away from the camera when doing tests, and it would completely lose it around a foot away from it. So you want to have your LEDs right on top of that camera if possible to get the best result for lighting up targets.
Question from the internet, is there a best camera to use?
I don't know if there probably is a best camera, but what we personally used was it was a Logitech. Well, we used a Microsoft USB camera. It was in a little case and it had a stand that came with it. We had to break that case open and just take the small camera chip out and put that in its own little 3D printed case. I believe in general Terry recommends Logitech cameras. They run like $60 or so. And they're reliable. We use those in some of our other vision processing things I've done outside of robotics. I'd recommend them too. So,
Add something?
yeah.
So one of the reasons why I sort of recommend Logitech cameras is that so different USB cameras have sort of different things that they allow you to do to them. And one of the issues that we were trying to do is we were trying to set exposure values. If you have like an auto exposure on a web camera, you can actually slow down your program quite a bit. So we wanted to have a set exposure value. But the Microsoft webcam was really weird in that it sort of jumped all over the place when we tried to set exposure values. But in our own like personal, like Chris said, outside robotics, when we started testing Logitech cameras, they were much sort of more consistent in terms of like setting exposure values. So yeah, our recommendation, I guess, is to try to use Logitech if possible. Oh yeah, also have like a wide angle view because we want to get. Because at the heart of it, we're trying to get the most things in the image as possible, so we can get the target in the image. If you have the target, you can sort of center that. But if you don't have the target, then image processing isn't going to really help. You can't find something that's not there.
So yeah, in general, wide-angle cameras with fairly flexible software that let you set values that you might need to. Okay, so other issues that you may have physically. Like I said, with flywheel shooters, which is what we used, when those wheels spin up, they create a lot of vibration. You might not notice it from looking at it, but if you have a camera mounted on the tip of one of those shooters, it will wobble a lot. And if it wobbles too much, your camera's going to think you're constantly aiming up and down, and it's going to keep issuing confusing commands to your robot, telling it to keep tracking up and down to correct for that, and it'll never fully lock on. So the way to account for that is to have a wider tolerance for what it will accept as close enough to the target. If you have the wider your tolerance, the less accurate you'll get. So you want to try and reduce on vibrations as much as possible because the more of those you have, it's going to be harder to hit. Another big issue is power supplies. So for the Raspberry Pi, we were initially using USB to micro USB power. We had wired it directly into the power supply for the robot, and we were using that. And that was causing us a lot of issues for two reasons. One, the cable was fairly long, and the longer your cable gets, the more resistance you have, and the system will struggle to provide the proper amount of power. If you have a Raspberry Pi wired up to a monitor or something, you may notice, if you notice a little square in the top right corner that's rainbow colored, that's their symbol for under voltage. It's a little counterintuitive, but that's what it means. If you see one of those, you want to look into your cables, take a voltmeter or whatever, and make sure you're getting the right voltage out of that thing, because that will cause you issues. It can corrupt your file system just like shutting it off improperly. And when you're actually using one on a robot, you want to take some cables and just physically like attach them to the Pi, like solder them in. There are pins on the Raspberry Pi that you can typically attach wires to power it that way. And that's much better for the robot because, especially in Stronghold, a lot of jostling, a lot of bumping, balls going where they shouldn't. If you hit your power cable and it gets unplugged because it's not a soldered-in connection, it's going to kill it. And then you'll be out for that match as far as vision processing. And then another small thing for when you're working on it outside of competition, you want to plug it in. There's a setting that's called basically force HDMI on. And what that does is it always makes the Raspberry Pi boots up, and it will initially search for any kind of connections like HDMI, VGA, whatever it has on there. And if it doesn't see an HDMI at first when it boots up, it'll just turn off that port and not look at all for the rest of its cycle. So if you don't have force HDMI on enabled, you need to make sure you have it plugged in and your TV or whatever you have it plugged into is actively searching for something on that port when you turn on the Pi, or else you'll have issues. So turning that on saves you a lot of trouble in the long run. I would do it first thing whenever you get a Pi and you're planning on using it. Okay, so now Rachel's going to talk about what's next.
All right, so there are a couple of things we wanted to do for next year to improve our vision tracking system. One of them is better debugging. As we mentioned earlier, we were using system.out.println for logging messages, and then we just capture them with the driver station recording. So what we want to do next year is actually use a real logging framework that will give us better output where we can rank the priority of messages and probably capture the messages in a better manner so that we're not just looking at recordings for logs. Another thing we want to do is possibly record video from the Raspberry Pi. So this year, when we were looking at video, we were just doing that through the driver station recordings. But if we record the video from the Pi instead, as it's writing the images, we will be able to actually view the video at its full frame rate and probably get a better view of what the Pi is doing at any particular moment in time on the robot. Another thing we want to change is we want a better communication system between the RoboRio and the Raspberry Pi. So this year we used network tables, but the problem with network tables is that it can only update 10 times per second. So but your robot code runs much faster than 10 times per second. I believe it's something like 20 milliseconds or 40 milliseconds for every run. So network tables is too slow usually. So what you want to do is use something custom, a custom communication framework that will let you control the frequency in your own code. So what we plan on doing is using UDP. And the reason we chose UDP over TCP is that with TCP, you have to deal with connects and retries and things that we generally don't really need for our application. With UDP, you just fire and forget, as they say. So if you drop packets or something, it doesn't really hurt us all that much if we're getting a new packet soon enough. So with TCP, you'd have to retry sending that packet, whereas with UDP, you just send it, and if not, it will retry soon enough. So a few more changes. One thing, we mentioned the safe shutdown thing earlier, but the way we were shutting down our Pi was by sending an SSH command after the match from the driver station laptop to the Raspberry Pi to tell it to shut down. But we believe that this method usually doesn't work because the FMS cuts network communications between your laptop and the robot after the match is over. So one thing we want to do is actually have the RoboRio signal to the Pi directly to shut down, because the RoboRio should be able to tell when the match is over, and once that's happened, it should automatically send the shutdown signal so that there's no problem with the FMS cutting communications between the driver station and the robot. Fourth change is that we want to not feed the camera input directly into our control system. So what we mean by this is that this year, lag may have been causing issues for us because between network delays would mess up the timing of our commands and cause hunting. So this illustration kind of demonstrates what we're talking about. So imagine that your robot at time t0 is moving to the right at it's moving to the right, but currently is pointed at 45 degrees. So the camera reads, it sees the target, and it tells the robot, turn right 45 degrees so that you can align with the target. When the robot receives that message at time t1, it will receive the command to turn 45 degrees, but if it turns 45 degrees now, it will go too far because it's already turned 25 degrees and is now facing 20 degrees. So what we plan on doing is, first, we want to synchronize the time between the Raspberry Pi and the RoboRio. And with that, after that, we want to send timestamped data to the RoboRio. Instead of just sending X and Y offsets, we want to put a timestamp on each X and Y offset pair so that we know when that data was collected. And what this will allow us to do is it will allow the robot to calculate, since the message was sent at t0, the robot was facing 45 degrees at t0. So if we figure out that we turned 25 degrees, then we will be able to account for that, adjust our message so that we know we only have to turn 20 degrees to align with the target. And this 25 degrees value, your robot should be keeping a buffer of the last known values from the sensors with a timestamp on each of those values. So that way, you can figure out what the robot was facing at t0, and you'll know that it was facing 45 degrees, and you'll be able to account for that. So
yeah, in summary, basically, what our conclusions we came to after last season of working on the system, in our opinion, the best way to really do a vision processing is a Raspberry Pi or another coprocessor combined with Python or OpenCV. Provides you a lot of flexibility, a lot of options. You can do a lot with it. HSV is probably our favorite way for doing all these colors as compared to RGB or other systems. It's very human friendly. Unlike RGB where you just adjust things randomly, HSV, you know what you're doing. And then when you build these things, you need to design them in advance, work with build or whoever you need to, make them robust, and have them well monitored for debugging and other purposes. Here's our contact information. If you have questions and want to talk to us about something later on, I'll leave this up here for 30 seconds or so if someone wants to write it down. Okay. And then in just a moment, we'll go on to questions. So if you have anything, be ready.
Question from the internet.
Mm-hmm.
How did you get the drivers to work with the Logitech cameras for the exposure control, specifically the V4L drivers? Do you know anything about that? May want to
Repeat the question,
Okay.
Mike, and give it to whoever.
Okay, so the question was how we made exposure work with the Logitech drivers. I believe it had V4L specifically. So I think I'll pass this to Terry to answer because we, like I said earlier, we personally use Microsoft cameras for our robot, but I know Terry's done a lot of work with Logitech. I've done some, but not as much, so I'll let Terry talk.
Okay, so you're testing my memory because I don't remember things very well. So there's a specific, because Raspberry Pi is a Linux machine, right? There's certain things that Linux allows you to do through I always forgot those drivers, such as like setting exposure values through what was? Yeah, V4L video for Linux. And so if you go online somewhere, like try Googling or something, but there's a specific line of code, not line of code, but there's a specific command line prompt that you can sort of enter into the terminal to set your the exposure value for like a particular webcam. The thing is, you could do that for Microsoft webcams, but Microsoft webcams are weird because sometimes you would start at like a 0 value for exposure and it's really dark. You set it up to be like, and you slowly increment, and it gets really brighter, but then it gets darker. And then you set it to like 1,000, then it gets super dark, and you set it to 500, it's super bright. It's weird. Logitech cameras are a lot more simple in that it actually follows that spectrum. Specifically, the cameras that I worked with and Chris also worked with were the Logitech 620s, I think, or something. It started with a 6. But those were the actual Logitech. Those cameras actually followed that whole, I guess, sort of exposure setting code. So in the actual Raspberry Pi code that we have, in the initialization period, we would just have a sort of sub-process run with that specific terminal command that has the exposure value we would want every time we would sort of boot up, and that code would sort of run. You want to add something?
Yeah. If I recall correctly, the command that you're looking for is V4L2CTL, like V4L2 control. So yeah, if you look into that, I believe you'll be able to set the exposure of your cameras programmatically and hopefully not run into any issues. So.
Okay, any other questions?
What about the Raspberry Pi camera? Did you consider that?
We did not consider the Raspberry Pi camera for this. I believe one of the reasons we didn't use it is because the cables it comes with, at least the default, are fairly short, and the camera is, I believe, lower resolution. Do you know the exact?
It is a little lower resolution. Sorry, it is a little lower resolution. In this case, it doesn't necessarily matter as much, just because we're using the Raspberry Pi 2, and the Raspberry Pi 2 it's not that great at processing, so we're actually like downscaling that image to be something a lot easier for the Raspberry Pi to handle. So you could theoretically use the Raspberry Pi camera just as well, especially the Raspberry Pi camera version 2 is also great. The only problem is that short cable. We didn't want to have the Raspberry Pi on the actual shooter arm itself, because that's a risk that we didn't want to take. So, yeah.
I've also been informed that our team was worried about shielding and with electronics and signals and all that. So.
Earlier you mentioned Pi network tables. Can you elaborate on this a bit?
Yeah, for sure.
So Pi network tables is just a Python implementation of the network tables library that you may be familiar with in FRC if you've worked with Smart Dashboard. Smart Dashboard actually uses network tables as the underlying communication protocol between the driver station laptop and the RoboRio. So you can, if you install the Pi network tables library, which is for Python, there are similar implementations for other languages, but you can use that to just connect to the robot's IP address and send values over to it, and you just look at whatever table you want to store your values in to look at the X and Y offsets and retrieve those on the robot side. So, yeah. Right.
Why did you specifically choose Python as a programming language for your vision with another language? Never heard before.
I don't see another reason why another language wouldn't work out just as well. I know OpenCV is supported definitely for Python and C++. So you could in theory use either of those languages or possibly others. We just personally use Python because it's fairly easy to pick up. We could teach it easily, and we've had some of our programmers don't like C++ as much. So it's just I believe it's mostly personal preference.
We also chose Python because Raspberry Pi sort of, a lot of Linux machines just sort of support Python right off the bat, and there's a ton of documentation that has sort of Python OpenCV code on there. Python's also very programmer efficient. You can type something really fast in Python and make it work very well. And so we decided to use Python because we were experimenting. We weren't exactly looking for the peak performance. We were just looking for the performance that would work the best in our situation.
As a side note for documentation, there's a website, I believe it's called piimagesearch.com. That's a guy, he does tons of articles about image processing stuff. We've used his stuff a lot in and out of robotics for all of our OpenCV work.
What's that website called?
piimagesearch.com, I believe. I'll write it up here real quick.
Sure. Any other question? Yeah?
Did you find yourself spending a lot of time optimizing your software to make it work better?
Yeah, okay, so a little. So when we're actually doing the actual OpenCV stuff, we're using the Raspberry Pi 2. And the Raspberry Pi 2 isn't a very sort of great processing, computation platform. So we actually had to downgrade our image resolution quite a lot, more than we would like. But there's a lot of different ways that you can actually, help, speed the program up. You can actually sort of blur your images and set different types of, filters on it, so you can have you can have sort of blockier pixels, so that makes image processing a bit faster. There's also, this process is a lot more mitigated now because the Raspberry Pi 3 came out. The Raspberry Pi 3 is way faster than the Raspberry Pi 2. I tested it, personally at home with my Raspberry Pi 3 using our own code, and actually ran way faster, especially since the Raspberry Pi 3 has 4 cores on it. It would only take up 25% of the processing power of the Raspberry Pi, our old code, while the Raspberry Pi 2 had to use the full 100% of the processing power. So you could, you could do actually a lot of multi-core processing with the Raspberry Pi 3 to drastically improve performance. So yeah. Yes.
What was the most frustrating thing to debug during the sequence?
I don't know. Yeah, that's probably yours.
Yeah, right. So the question was, what was the most frustrating thing to debug during the competition season? And I would have to say the MDNS issue took us quite a while to figure that out because when we were doing it in our testing environment, MDNS worked perfectly because we didn't have the interference of FMS in the way. But when it went on the field, we didn't understand why we couldn't ping the Raspberry Pi or anything. And we later switched to static IPs and found out that that issue was mitigated. So that's probably the most frustrating thing.
So my personal sort of frustration was setting exposure value for the same reasons I said before, but yeah, it was kind of frustrating.
To elaborate on the MDNS versus static IPs issue, because Rashad kind of downplayed it a little bit, that debugging process took place across, I think, 80% of our matches at one of our regionals. So it was a series of play a match, didn't work, try some fixes, play a match, didn't work, try some fixes. So that one video we showed where it first started working, that was one of our last few games of that regional before the playoffs. Yeah, KSU. So that was a little bit harder than it was originally described.
How does the coordinate system work in OpenCV?
Okay, so the question was, how does the coordinate system work in OpenCV? So the coordinate system works similar to, well, I'm assuming it's a standard for just computers and coordinates for images and websites. So your top left corner of your screen is 0, 0. As you go down, Y increases. As you go right, X increases. So if you have a 1080 by 1920 screen, then top it would be 0, 0. Bottom right would be 1080 by 1920. Well, yeah, or reversed, but.
For teams that don't have access to like a Raspberry Pi or anything like that, how would you recommend they go about making a system like this?
My personal suggestion is if we didn't have access to a Raspberry Pi or some kind of coprocessor, the next best option, I suppose, would be to run it on the laptop. While it's not ideal for the reasons we covered, you at least have the processing power and you won't be slowing down your essential robot code. But again, we highly recommend a coprocessor.
Yeah, I was just about to mention, it only costs $35, and there's a Raspberry Pi Zero that costs $5. And you can run a neural network on a Raspberry Pi Zero, so I'm sure you can run like HSV filtering on a Raspberry Pi Zero. So yeah.
Can you go back and discuss PIDs a little bit more?
Yeah. PID is a fun question.
Yeah. So PID has to do with, it stands for proportional, integral, and differential. And it's what we use to target our motors. So when we have our shooter, on our shooter, we don't have like a servo or anything that can precisely measure you can't precisely set the angle on something like a shooter. So with PID, what you do is you give it an input that's based on an encoder, for example, that's attached to your shooter, and you put the PID output as your motor. And then what you do is you have to tune the P, I, and D values to, so what that does is it takes, when you give it a target value, such as like 120 degrees, it reads your encoder value, which would be something like 90 degrees, and it would subtract that, come up with an error of 30 degrees, and it would multiply it by the P constant and do an integral with the I constant and a derivative with the D constant of the error. And it would calculate out a path for a motor output that would hopefully get you to the right place. So Chris here has a drawing of.
So yeah, basically, the way PID works is you have a motor and some way of measuring a statistic on that motor, like distance. And you go into the code, and a lot of this is pre-set up in WPILib. You can do, this is difficult, but it comes kind of pre-built. And you can tell it, I want to go to this target value on this sensor. And it will start running that motor, and as it runs, it will continuously correct itself to try and best hit that target. So like it'll start very fast, and it'll ramp down as it gets to it. And this requires basically the P, I, and D values. You have to tune them to get to this kind of result. If you do it badly, then you'll go up and down way past your target, or you'll go too low and never hit your target. So it takes a lot of tuning across practice runs to really get this kind of graph here. So yeah, PID is a, yes?
Is it ever
Maybe. I don't think we've ever had a perfect PID. So if you want like really exact motion, you would want to do something like motion profiling, but we're still working on that personally. It's a very complicated topic. PID is complicated too, but motion profiling is another universe from that.
I just wanted to mention the reason we use PID and not something simple like just move the motor until we get to the right position is because with that you can run into problems like overshooting, which it would be basically the same way as the like a PID that's not correctly tuned. So it would just go over or under and not hit the target exactly, which is why we use PID. I just wanted to mention that's the reason.
Aside from PID, were there any other algorithms that you used in order for tuning your vision system?
What do you mean by that question?
I don't know. Like filtering, like some sort of filtering that you used in order to filter out data values or something like that.
Or maybe like, hey, we shot the wrong target because like it wasn't a target.
Oh, okay. So, I mean, the first thing I guess I would say is that the sort of demo of we showed with the HSV thing, we use that to at least set our HSV values, and we try to do that fairly regularly because HSV is pretty stable and pretty nice at like finding objects, but sometimes lighting conditions change and something might break. Maybe the LED burns out, so you have to switch it out, and the LED brightness isn't going to be exactly the same. So we try to tune our HSV value. So that's like our first step in terms of like tuning our vision processing thing. And the second step is, I guess, is tuning our offsets. So we actually took our robot to a practice field, and we had the drivers actually manually set up some shots that we knew we were going to hit. And we actually recorded the camera positions of those shots. We've recorded the position of the target, and we recorded the center of the camera. And we actually compared those two offsets, the X and Y offsets. And using a bunch of data points, we actually created a graph, and from that graph, we made an equation. Okay, yeah, math. So, that was our equation, and from there we can basically predict, what our shots were going to be like. And so we would have that inside the Python code on the Raspberry Pi, and that we would sort of feed the coordinates into that equation and hopefully get the correct offsets out. But sometimes those equations don't necessarily work. So I guess we would have to turn maybe, if it was like a linear equation, we would tune like the y-intercept or like the slope to just sort of fiddle with it a little. Especially if the camera gets moved, then we have to redo everything. So yeah, so those were the general tuning steps that we took.
No.
Did you ever have to account for like shooting? So say if you're looking at the target from an angle, did you ever have to account for like a change in dimensions of the contour box?
We did, because basically the way our system worked, as we showed in pseudocode a while ago, was we searched the largest contour. And so if we were lined up between two targets, we'd sometimes have issues where it would move to aim at one, and then the other one become larger, and it would go back and forth between them like that. So we had to work out that. We tried to avoid those kind of angled shots, though, because they were a very difficult edge case.
When you had a 45 degree, and like when you realized you need to turn 45 degrees, the time was off, you have to make an equation to fix the ratio of time that you realized right?
We did not implement anything like this system. That's one of our future goals. We just effectively had to move kind of slower, because if it went too fast, we'd have these kind of issues. So we just kept it moving slowly for now.
Do you know if you can run TensorFlow on a Raspberry Pi?
So, okay. I like image processing, and I'm into machine learning, so I can actually answer that question. Yes, it can. It can actually run on a Raspberry Pi Zero, but not very fast. You can run it on like a Raspberry Pi 3, but it's not going to be very fast. Stuff like machine learning and TensorFlow, you really need GPU power, and the Raspberry Pi is not GPU power at all. You would have to use something like an NVIDIA Tegra or something like along those lines. That is just pure GPU power. Yes? Oh, TensorFlow. So TensorFlow, for those of you who don't know, it's the machine learning library that Google made. It's the thing that powers all of their sort of image recognition stuff. And a lot of different companies use it. I think Twitter and Facebook also use it at some point. But TensorFlow, it's a neural network machine learning library. So I can't really explain how that works in this because it's kind of out of scope of this presentation. But basically, you do a lot of matrix multiplication in TensorFlow, and a lot of GPUs are really great at matrix multiplication. So you need a good GPU to run TensorFlow, and Raspberry Pi doesn't really have a great GPU. So yeah. So it can run. Don't recommend it. Get like an actual GPU machine to actually if you want to run that. So yeah, Chris is trying to draw a neural network. Okay.
It's a lot of.
Imagine a lot of dots, and they're connected together, and data goes from one end and gets manipulated to come out at the other. Like machine learning, essentially, is you give it input and it gets you an output. Except how that works is kind of complicated, but that's your input, and these two are your outputs. Okay.
Take you to process a frame.
On our Raspberry Pi 2, I would say it was taking what, maybe 1/10 of a second, 2/10 of a second.
I forgot the specific data, but it was like we were computing 100 things.
I would say we were probably running roughly 15 frames a second on average.
What's your biggest latency between like something getting captured on the camera and actually moving the robot? The network in terms of the image processing.
Since we ran on a coprocessor directly wired into our robot's internet system, our largest break in latency was definitely when we were actually processing the image, because like Terrace mentioned earlier, we had to scale down our images a lot, and even then we still had some delay. So most of it was our process, basically processing the image, finding the contour, and then sending that data. That takes a bit of time.
I know there was some talk during the season about switching to C++ for next season, or sticking with Python. So have you guys come to a decision, or are you guys still talking about it?
This is the starting time.
Well, we're not programming our robot in Python. We're not programming our robot in Python. We did Python for the Raspberry Pi because it's a Raspberry Pi and Python works very well there. So there's some talk of doing either Java or like C++ as our main robot code, programming thing. And C++ runs a bit faster, and we could do a lot of cool things in C++ that we couldn't do with Java. I think we're going to stick with Java just because, if you don't know, us three are the programmers for 1261, and 2 of them are seniors, and I'm a junior. So I don't want to be alone next year. And C++ is kind of hard to teach, So I think we're just going to sort of stick with Java. So that's the consensus? Yeah. So yeah.
Yeah.
So Rashad wants to talk.
Yeah, I just want to mention, I don't think Python is supported by FIRST and WPI. So if there are libraries that will allow you to code your robot in Python, but I don't think they're supported. So if you have trouble with Python library, FRC won't really be able to help you all that much. So that's another reason we're not considering it for our robot code.
Yeah, in general, the C++ method is a lot more team run, and at the moment we don't really have the programming resources to dedicate to building that kind of system, but it's definitely something that we have in mind.
You mentioned earlier about doing the image processing on like your driver station. Have you tried that, and do you know how much that impacts your latency?
We have not tried it. We have done processing on a laptop using grep. We did some early testing with that in the beginning of the season. But with the 7 megabyte bandwidth cap, it's dangerous to do it because depending on how much data you have to send over, if you, like Terry mentioned earlier, if you hit that 6 megabyte point, they start seriously throttling what you can send so you don't hit that 7 point. So I assume in that case, you'd have a lot of latency issues. We do not personally know how bad it would be, but I would assume it would probably require a lot of working around.
So I've been informed that if we have if we're sending less than 6 megabits, then it's like 10 millisecond delay or latency, but if it's over 6 megabits, then it's like 80 to 90 millisecond delay.
As a final thing for that, I think the biggest factor on using it on your laptop is how much resolution you're willing to sacrifice, because the higher resolution you get, the more and more bandwidth you have to take, because you're sending an image from a camera on the robot across the bandwidth to your laptop, processing it, and then sending more data back, and they're constantly happening, so that can be a lot of bandwidth, so you have to really cut down on your image resolution.
Are you guys making any changes to the system for grits?
Not any major changes. We're going to be doing some small tuning, and we're going to be upgrading from a Pi 2 to a Pi 3 because it runs much faster. But other than that, we're not doing any major overhauls between now and grits.
Is it better for it to be like exactly that city? So, I don't know, you said it was 10 megabytes?
You can have 7 megabytes. The hard cap for sending over FMS is 7 megabytes bandwidth. Megabits, my bad. I get it mixed up. But it's 7 megabits cap, and once you hit 6, they start seriously throttling you. So like you start losing certain signals. They try and keep it so only your robot stuff's going through, I believe.
How did you calculate the angle for your turning? Were you just counting pixels in your field of view?
So calculating, basically, yes. We kind of made the pixels into an unofficial unit of measurement for the robot. It basically it literally just receives an offset, and it sees that number, and as it turns, it knows that number gets smaller, and it keeps turning until that number is small enough. So we are literally just counting pixels in the code, because it would be really inconvenient to try and actually turn into an actual unit.
So, could you elaborate on some of the problems you had at KSU with the lights and stuff like that, and things you may have done to eliminate white noise?
I don't think it was so much of it. Oh, it was kind of an issue at KSU, but it was a much bigger issue at our event at Georgia State, I believe it was, where they had we had huge floodlights that were on above the field, and they were shining directly down on each goal because apparently we couldn't do anything about them, or they didn't want to, so we were told it wasn't going to happen. And so these huge lights were basically they were making this intensely bright light going on the camera, and it was really confusing the system. So what we ended up having to do to work around that was we had to turn down our exposure a lot, which is why in a very early image you probably don't remember, it's basically everything is black except for LEDs and the stuff bouncing off the retroreflective tape, because if we see anything else, that means our exposure is way too high. And basically, with that exposure turned really down low, we can then easily differentiate between intense white light from a floodlight and what becomes now a nice green glow instead of the intense spotlight it actually is. So we can actually see that and target it properly.
Minimum timing frame? You had to be there for at least a half second.
Oh yeah, you want to talk about it?
Yeah, so the thing is, with our, one thing we did to solve that problem with the floodlights confusing our vision tracking system was that we had we made sure that the robot could, we would only shoot if the robot could see a particular target for, say, I believe it was a quarter of a second or half a second or something like that, because the floodlights, when it saw the floodlights, it would occasionally track it, but it wouldn't track it consistently. So by introducing that minimum time, we were able to make sure that what we were looking at was actually a target, because it would track much more consistently.
Yeah, basically all that was when you see a target, wait like a quarter of a second. If it's still a target, then we track it.
Are you planning on overclocking your Pi?
I don't believe so, although it would be fun if only for the fact that we could try and design a water cooling system at that point. We've had... See, if it's a water game, then maybe we could have little pumps going out of the Pi into the pool itself, and we could cool it that way.
Another interesting thing about the Pi 3 though is that actually it's the first Pi that actually heats up significantly. Like the actual chip heats up to like 100 degrees Celsius. It's supposed to be limited at like 100 degrees Celsius. It starts throttling at like 80 degrees. So I really recommend if you're using a Pi 3 and if you're doing some intense stuff on there, like put like a small sort of heat sink on there. It'll actually improve it quite a bit. If you actually put like a full CPU heatsink, I think you can improve like performance by 50% or something ridiculous. But yeah. Yes?
Why did you use a Raspberry Pi instead of something like a Beagle board or a Beagle board?
I think Raspberry Pi is generally faster than a Beagle board, correct? And it was available. And I personally work with Raspberry Pi. So when we talked about the whole divide and conquer approach, I was the guy that was working on the Python and OpenCV thing on a co-processor, and I had a Raspberry Pi, so that's the sort of, I knew how to use it on a Raspberry Pi. That's generally the route that we took with it. Here you go.
Any more questions? Or okay, so yeah, thanks for listening to our presentation. Hope you learned something, and try doing vision tracking in your next year's robot. It's really powerful stuff. You can do a lot with it.
Thank you for listening.
So a big thank you to 1261 for coming and presenting on the Raspberry Pi machine vision. Again, we'll be sending out a post-session survey, so let us know how we did, if there's anything we can improve. We'll also be sending out all of this information, the slideshow. We'll send a link to this website and any other supporting information in that email as well. So if you missed it or if you want to go back and review it, it'll be in your inbox soon. So if you have any questions, they'll be here and we'll be here for a few more minutes. Thank you guys for coming. See you at Grits next weekend.